So like I was saying, if you look at this mechanism and if you look at the product outcome, the first step is a proton transfer. You have a proton transfer. Then you have a nucleophilic attack. See? And subsequent loss of the living group. Okay? Now, after you have the formation of the alkyl halide, this stops here. Why? It stops here because we know that aryl halides or a aryl living group, no SN2. You can have an SN2 with an aryl group, no SN2. So that's why it doesn't go any further. Okay? To promote cleavage, HI and HBr are generally effective, and the reason is because HI and HBr are beta nucleophiles. They are beta nucleophiles. Right? The Br minus and the iodide are beta nucleophiles. Explain the trend above. Explain the trend above. We expect that the most nucleophilic is the iodide, and the least nucleophilic is the fluoride. Right? That's something we learned from from organic Chem12B. Now, why is the acid considered an acid promoted rather than acid catalyzed? The reason is because in the acid promoted, the acid is used up. Okay, the acid is used up. So if here we have to predict the product, right? So in the first case, you have protonation or proton transfer, and then you have the formation of the first alkyl bromide after nucleophilic attack and loss of the living group, and then you have the second protonation of the oxygen, in which you have the formation of this, and then you can see that this forms the alkyl bromide. Okay, and that's because this is an alkyl, a cycloalkyl. With cycloalkyl groups, you can have SN, you can have SN2. SN2 is possible, but with aryl groups and vinyl groups, SN2 is not possible. Okay. Now, so recall also from 11.9 that ethers can undergo auto-oxidation because of these hydrogens here are susceptible to auto-oxidations, right? And so they form hydroperoxide, which can be explosive. So the laboratory sample must be frequently tested for the presence of hydroperoxide before used. Okay, and this is just the mechanism of the reaction. You can see the initiation, formation of the radical, and you can here see the propagation, the presence of molecular oxygen, and after that you can now see the hydrogen abstraction to give you. So you can have the hydrogen abstraction to give you this radical, and the process continues, and then you have a termination. See, and we said that the propagation step is always the step in which the step that add up to give the overall reaction. The termination and the initiation steps do not add up to give the overall net reaction. Now let's talk about naming epoxides. Now naming epoxides, the epoxide is called epoxide are cyclic ethers, and the size of the ring determines the parent name of the molecule. So here you have an oxy ring for 3-membered, oxetane for 4-membered, oxolane for 5-membered, and oxane for 6-membered. Now, oxy rings are also known as epoxides, known as epoxide, 3 members. Now, which cyclic ether system do you think is the most reactive? Of course, the oxygen is going to be the most reactive because of significant strain. It has significant strain, so it's going to be the most reactive. See? Now, when we want to name epoxides, right, there are two ways of naming it. You can either name the epoxy group as a substituent, in this first case, right? And then, of course, you have to consider the parent. The parent in this case is pentane. And then at the 2,3 position, you have the epoxy group, okay? And at the 3 position, you have an ethyl. At the 2 position, you have a methyl, right? And then at the 2,3 position, you have the epoxy. Notice that the epoxy is just before the parent. It's not alphabetical. It's actually just before the parent, okay? Or you can call it an oxyrane. When you're calling an oxyrane, make sure you number the oxygen as number 1, number 2. I'm sorry, number 2 here because of the ethyl group, right? And number 3 because of the methyl group. So you have 1, 2, 3. So in this case, this is going to be 2,2 diethyl, 3,3 dimethyl oxyrane. So all these are considered to be substituents. So they're considered to be substituents. This is a great example, which I've already done. So first of all, you have to determine the stereochemistry, right? And then you have to look at how it is numbered. See, you have to look at how it is numbered. This is very important. You have to number it to like a double bond: 1, 2, 3, 4, 5, and 6. So at the 3 positions, the ethoxy group. At the 1 and 2 is the epoxy, and then you have the cyclohexane. Okay, this is another example, in which case you talk about stereochemistry first, right? And then you have the ethoxy group at the 3 position, and then 3, 4 position is the epoxy, and then the hexane. Notice how it is numbered. See, it is numbered 1. You have 1 here. This is how it is numbered. You have 1, you have 2, you have 3, you have 4, you have 5, and you have 6. You see? And then here, this is if you want to call it an oxyrane. If you want to call it an oxyrane, you have to name it slightly differently. You see? Because now you have to count. You have to count. So this is number 1. The oxygen is number 1. This is number 2. And this is number 3. See? So first you begin with the stereochemistry, right? And then you want to go ahead and put at the 2 position you have this whole substituent, and at the 3 position you have the ethyl group, and then the parent is the oxyrane. So that's basically how you do it. This is another example which I just concocted, right? You can see again that at the 2 position you have the ethyl, the 2 position you have the methyl, the 3 position you have the propyl, and they have oxyrane. So these are just a way to name different types of epoxides. You can either name it considering the epoxy as a substituent, or you can name it as a parent, in which it becomes the oxyrane. Now recall from section 9.9 that epoxides can be performed when an ethyl alkene is treated with a peroxy acid. See, an alkene is treated with a peroxy acid. See, and an example of a peroxy acid is MCPBA. See, that's MCPBA, which is meta-chloroperoxybenzoic acid, right? And then once this is prepared, you get the epoxide. And notice that it always proceeds with retention of configuration. So the configuration is always retained. Okay, configuration is always retained. Now, epoxides can also be formed via halohydrins. And in the halohydrins, you have a halogen and a halide. I'm sorry, no, a halogen. I'm sorry, and a hydroxy. A hydroxy group. Okay, that's a halohydrin. So basically, you're adding water or the OH and the bromine, in this case you see bromohydrin. And in the presence of the base, you now have the reaction undergoes a ring closing and you get the epoxide. Okay, and how does this form? First of all, you have the base abstracting this proton, and once the proton is abstracted, the alkoxide acts as a nucleophile and then attacks via an SN2. So you have an intramolecular SN2 with the formation of an of the epoxide, which proceeds via an inversion of configuration, and thus we know is typical of an SN2 reaction. Now, access the overall stereochemistry of the epoxide alkoxide through the halohydrin intermediate. You can see that the reaction proceeds with what? Retention of configuration. So if you start out with a cis, whether you use MCPBA or you use bromohydrin or halohydrin in presence of base, you still get the cis. So it proceeds in either case with retention of configuration. So please make a note of that. Now, let's look at enantioselective epoxidation. Okay, enantioselective epoxidation. The epoxidation methods we have discussed so far are not enantioselective. That's because you get a mixture, a racemic mixture. You get a racemic mixture, whether you use MCPBA or you use a halohydrin in the presence of a base, right? To be able to impart enantioselective epoxidation, right, you have to use a chiral. You have to use a chiral catalyst. You have to use a chiral catalyst because you see the epoxide can add either from the top face or the re face, or can add from the bottom face of the side face. So you can add from either face. You see? So how do you do it? So you have to use a chiral catalyst. And so the guy by the name of Sharpless developed the Sharpless epoxidation, and he used titanium tetraisopropoxide in the presence of either positive DET or negative DET. But the requirement is that this reaction works only for allylic alcohols. This works only for allylic alcohols. Okay, and I think it's because of the presence of that OH where it can chelate nicely. Okay, the desired epoxide can be formed if the right catalyst is chosen. Note that the position of the OH group. So the right catalyst. Now, if you use the positive DET, the epoxide comes from the top face. It comes from the re face. While if you use the negative DET, the epoxide is formed from the side face. See, so you just get one epoxide. You just get one epoxide. See, and that makes for enantioselective epoxidation. You get just one enantiomer and not the other. Now, okay, so you can see how the top face, the re face, if you want the epoxide come from the top, you have to use DET positive. If you want it to come from the bottom of the side face, you use negative DET. But remember, it only works for allylic alcohols. Only works for allylic alcohols. Okay, only works for allylic alcohols. Now, ring opening of epoxide. Because of the significant ring strain, epoxides have great synthetic utility as intermediates. Now, we can propose some reagents that may react with epoxide to provide a specific functional group. For instance, if you want to make a halohydrin, you can use HBr. If you want to make a diol, you can use this. If you want to make a diol, if you want to extend the chain, right, of an alcohol, if you want to make an alcohol with an extended chain, you can use a Grignard or you can use an acetylide anion. Okay, so all this will help you increase the tools that you have for inorganic synthesis. Now, strong nucleophiles readily react with epoxides. Right, they can attack either of these carbons because each of these carbons is electrophilic, right, and that will lead to, in this case, if it's attacked by an OH minus or an hydroxide, then you get the diol. You get the 1,2 diol. Okay, right. Now, you get the 1,2 diol. So in general, alkoxides are not good living group, but because of